don't know. Finals week's going on. It's hard to find classrooms. Yeah. Yeah, the Geek Central there. Well, they all hang out. Okay. Big Bang. The Big Bang Theory. You could film it in that room. But anyway, all right. Now, so then if you come here, you go, oh, cool. Look at this. Study guide for solutions. You open this. Boom. You open this. You open this. There we go. All right. And I've put solutions for a select number of the problems there. Okay? So that you can go, oh, okay. And you can work through them. All right? So that's there for you too. All right? Okay. So now don't just count on that and read those and go, oh, okay, I've got these memorized. That's why you study for a psych test, not for a physics test. All right? Second here.
Are you going to upgrade our grades on black holes?
Yeah. Yeah, like put in the that's on the announcement too. By 3:30 I'll have your Weeblos on Wheels stuff in there. Oh, the homework stuff? That'll be probably Monday or Tuesday. We'll get all that on. Yeah. Yep. So that when you take, and your lab grade will be in there, all that stuff. Okay? All right. So let's just start then. Let's go ahead and finish chapter 26.
Can we go over the last question about the black hole?
Yeah, we're going to talk about black holes here in a minute. All right? Okay. Let's just take a look at some of the examples. 26 here. I just as soon use this guy. Does that work? Not too good. I want to turn the lamps on. There we go. All right. Now, let's take a look at some of the problems, because I got questions from some of you on that. I think that whole black hole thing is kind of cool. All right, what the radius is of a black hole. In fact, let's do this. What is it? The Schwarzschild, the Rothschild. I always tease the astronomers, call it the Rothschilds, but that's not right. It's a Schwarzschild radius thing. And what that says is, this is where you have the event horizon, where r equals 2gm over c squared. Okay, and that's based on the escape velocity, v escape velocity. One of the nice things now to prove all this stuff, the mathematical arguments that Einstein came up with to prove all this stuff, he had to use a thing called tensor calculus that was developed by, oh man, now I'm in trouble. I forgot the other mathematician's name that came up with it about the same time, about the late 1800s or so. But for the most part, most of the stuff, even if you take like a advanced, well, like when we get into the handful of you that are taking Physics 350, most of it we can do with algebra. We can do it with algebra, so it's not bad. And because they base that on escape velocity, which was the square root of gm over r squared, right? Yeah. Well, what was it? I better double check here in the book, real quick. Sorry. Oh shoot! I knew I'd get ahead of myself. Hold on one quick second, because I also have to. 2gm over square root of 2gm over r. There we go. Square root of 2gm over r is escape velocity, and so that's where they got this. And that's the event horizon. That means that's where nothing escapes, no light escapes or anything like that. And the gravity, the amount of gravity that you start to feel there is pretty intense. In fact, it's so intense that I was reading one article about some of their ideas of what happens at the event or horizon, and we all turn into like two-dimensional figures all spread out in an infinity type thing around this curve. So I was like, okay, whatever. But anyway, pretty much what happens is you get crushed. All right. Disney made a movie called The Black Hole about 30 years ago that was absolutely ridiculous. Anyway, as Richard Pryor said, he thought it was a movie about Lola Falana, but it wasn't. But so they had the they actually went into the black hole and came out the other side. It's like, yeah, right. Anyway, all right. And I was even in high school when that was made. All right, and I knew better. But anyway, let's take a look at one of the problems that could come off of this. And basically, here's one. Did we do this one? Hold on. I had a bunch of them worked out here. 30 and 32. Oh, there we go. Here we go. I'm sorry. 40. Let's look at problem 40. I kind of ran into it. All right. It says a black hole has an event horizon of radius of 5.00. So R equals 5.00 times 10 to the third meters. Okay? All right. And one of the things I did today was I went, well, this looks awfully funny. I've got this universal constant of gravity. I've got kilograms, and I've got divided by c squared, meters squared per second squared. I wanted to see if it actually worked out to be meters, and it does. So I checked the units, and it was right. But it was it kind of led into some insights, too, when I was just doing that little drill. So anyway, it says that there's the event horizon. Now it says, what is the mass? What's the mass? Now, let's go ahead and calculate that thing. Well, it shouldn't be too hard. If we've got R equals 2gm over c squared, this is a problem that could show up again. So the mass is just going to be rc squared over 2g. Okay? And when you calculate all that in, let me just go ahead and do this real fast. Show you something here. All right? On the calculator, I know this is going to be like snooze city for some of you. And I also have to get to relative velocities today. So this will be where we kind of stop on this one. All right, can you see that? Yeah, it's not too bad. It's not too bad. But here you go. Now, here's the way I calculate these things. I put everything in parentheses. So basically, I've got 5 second e to the third times, parentheses again, 9 second e to the 16th. Now, where did I get that? Right, it's 3 times 10 to the 8th squared. Remember, you got to square both things. So it's 9 times 10 to the 16th. Okay? So that's the speed of light squared is 9.00 times 10 to the 16th. I know that's kind of hard to see in there. It's kind of, there, that's a little better. Get the light shining on it just right. That's a little better. All right, divided by, now I put this in parentheses, 2 times, put this in parentheses, 6.67 second e to the negative 11, double parentheses. And now I've taken care of it. Boom! 3.37 times 10 to the 30th kilograms. Yeah. You get some BANs here, big ass numbers. When you're dealing with relativity, you get some huge numbers. All right? And so the mass is equal to 3.37 times 10 to the 30th kilograms. Now, that may not mean anything to you. Let's put it in this terms. The mass of the sun is equal to 2.00 times 10 to the 30th kilograms. That's the mass of our sun. All right? So this little black hole that's only basically a 10K across, 10,000 meters across is all it is, has this amount of mass. Extremely massive. Extremely massive. And then the other kind of cool question that they ask from that is, determine the gravitational acceleration it produces at a distance of 5.01 times 10 to the third. This distance away from it. Okay, so let's take a look and see what the acceleration let me think now. Remember A is equal to gm over r squared. Remember that? Remember that? What we got to do is find the acceleration. All right, so we've got the mass. So we have the mass here, and now we've got to find the acceleration. All right, and we're going to let r equal 5.01 times 10 to the third meters. 5.0. In other words, we're not quite into the event horizon, but almost. Okay, we're not quite into the event horizon, but almost. So let's figure out what the acceleration is at that point. And so basically all you got to do is 6.67 times 10 to the negative 11. Remember, I do all these in parentheses, times 3.37 times 10 to the 30th kilograms, and then divided by, in parentheses is the way I would do this, is 5.01 times 10 to the third, close my parentheses and square it, close my parentheses again. And I can't go wrong that way. Okay? Because a lot of times I think what happens to some of you is you do this, divide by this, and then hit the squared, and it gives you all of this squared. And then that's not the right, so a lot of it is PIMDOS mistakes that I think we make when I get these emails saying, I can't get this thing to work. And I'm like, it's a PIMDOS thing is what you're suffering from. I can just tell. I can tell by the frustration level that you understand the physics, but you're having trouble with crunching the numbers. All right, and so when we do that, I'm going to do this real quick because it's just kind of a cool, I just like the big numbers that we come up with here. Second e to the 30th divided by, I better follow my own advice here, double parentheses, 5.01, second e to the third, close parentheses squared, close parentheses, boom. Oh my goodness! A is equal to about 8.9 times 10 to the 12th meters per second squared. Yeah, wow. So, wow. You'd be pretty heavy if you got close to that. Saying that, well, let's say you're a male or something, a rather large male here, so you're 100 kilograms or something like that. Multiply this by 100, and that's how many newtons, that's your weight, would be about 9 times 10 to the 14th newtons, which is pretty heavy. All right. Okay, so that's how you do that. Now, the next thing that I've got to show you, because I think it's really cool, and it's what it's relative velocities. Okay. All right, and I don't like the way the book described it very well. I mean, they did an okay job, but let's take a look at this situation here. Let's take a look at this situation here. All right, everything's going to be based on, I'm an observer on the ground, okay? Observer on the ground. I always do this. I always draw a little man standing on Earth, on the ground, okay? Little man standing on the ground. All right, now, here's what he sees. Here's what he sees. He sees a rocket, all right, a rocket launched toward Earth, launched outward from Earth, has a speed of 0.1 c. Okay, so we launched this rocket. Here we got this little rocket, okay, and it's going at 0.1 c, that direction, which gives me, now this is, we'll call this A, and this is the velocity of A relative to the ground equals positive 0.1 c. Okay? Now, they've shot this rocket at a meteor that's hurtling towards Earth. Okay? This meteor that's hurtling towards Earth, they're going to try and blow it up. All right? And basically, here's our meteor over here. and it's hurtling towards Earth, and its velocity, and it's b, velocity b relative to the rocket is negative 0.25 c, because here's what it says. Here's where the problem reads. It reads that the rocket is directed toward an incoming meteor that may hit the planet. If the meteor moves with a speed of 0.25 c relative to the rocket and directly toward it, what is the velocity of the meteor to this guy on Earth? In other words, what is the velocity of b relative to g? Okay? What's the velocity of b relative to g? All right, here's how you do that. Now, what would Newton say? What would the Newtonian answer be? What's that? It'd be what? You'd add them, so you get 0.15 c, right? In other words, it's hurtling towards Earth at 0.15 c. All right, well, let's start with Newton. Einstein at least started with Newton. He said, okay, so the velocity of b to g is equal to this. It's the velocity of a to g. See, I like my notation better. Velocity of a to g plus the velocity of hold up. Yeah. Of a to b. Hold on a second. Velocity of b to the ground. Yeah, this is all right. This is a to g, b to a. All right, because what I wanted to, yeah, velocity of b to a. There we go. Sorry, I lost my mind there for a minute. But actually, what I want to do is I want to rewrite this. I want to do this again. I want to do it this way. Velocity of b to g. Here's where I got stumped. B to a plus velocity of a to g. Now, why did I do that? Because I want my two guys right here, my two subscripts right there to cancel, and that's how I get b to g, okay? Then I divide by, here's what you divide by. 1 plus VBA times VAG divided by c squared. Which basically, since this is 0.1 c and this is 0.25 c or whatever, the c squareds cancel. So it basically boils down to this. Velocity of b to g equals VBA plus VAG divided by 1 plus VBA times VAG. Okay? And when we do that, when we put in our, so let's run the numbers. So we've got b to a is negative 0.25 c plus 0.1 c divided by 1 plus negative 0.25 c times 0.1 c over c squared. There it is. And so the c squareds cancel. And that's what I'm left with. And when I run these numbers, I get negative 0.25 plus 0.1 equals divided by parentheses. Now here's how I do it. I put parentheses 1 plus parentheses negative 0.25 close parentheses 0.1 close parentheses twice. Boom. There it is. Equals negative 0.5154 c. Okay? So it's actually going a little bit faster than we would think, than what Newton predicted. Okay, it's going a little bit faster. Now, let's take a look at this situation. Here's one that might come at you. All right, here we go. Let's take a look at this guy. Gonna have my little guy on the ground again. All right, and I've got my Starship Enterprise here. All right, so my Starship Enterprise there is going at 0.7 c. So the velocity of A in relation to the ground equals positive 0.7 c. That's how fast it's going. Then I've got like my Klingon destroyer, which I can't draw without it looking obscene. So we'll just make a regular airplane. All right, going this way. And this is going, the velocity of b to the ground is going negative 0.8 c. Okay? All right? Okay? Now then, what would be, and so now what I want to do is I want to find, now this is its velocity relative to the ground. This is its velocity relative to the ground. What I want to do is I want to find the velocity of A in relation to B. That's what that means. I want to find the velocity of A in relation to B. Again, what would Newton say the velocity of A in relation to B would be? Yeah, you would add these two, and it would come out to be 1.5 c, right? Because it's coming at him in a negative way. It's going negative 0.7 plus his negative 0.88 c going the other way. And so it'd come out to be 1.5 c, but nothing can surpass the speed of light. Okay, so something's got to give here. All right, and so here's what we do. We're going to find VA to B. So what we do is we go VA to B is equal to VA to G plus V, what are the subscripts I need to put down here? If I want to get A to AB, I've got AG, so what subscripts do I need to put down here? GB, exactly, GB. Uh-oh. Now hold on. BG is negative 0.8 c, so what do you think GB is going to be? Positive. So when you flip the subscripts, flip the sign. All right? And our book doesn't explain that very well. When you flip subscripts, flip the sign. Okay? All right? And this is also divided by 1 plus VAG times VGB. Okay? That's what the velocity of this thing. So, when we plug all this in, we get 0.7 c plus 0.8 c equals 1 plus 0.7 c times 0.8 c. Well, those c's cancel, so we just leave those out. And we come up with 1.5. Look, we've got 1.5 divided by 1.56. Is that greater than 1? No, it's less than 1. So even though, so that's the, so we come up with 1.5 c divided by 1.56. So 1.5 divided by 1.56 equals 0.96 c. That's the velocity of A relative to B.
How can you switch the velocity of B to B?
Because I want to get AB and I want to cancel these two guys. And the way I cancel them is the last guy here and the first guy here get canceled. Okay? So I had to switch him, and so when I switched him, he became positive. And that makes sense. If you're in this space shuttle here, or this Klingon warship or whatever, that Star Trek thing is coming at you at 0.96 c in the positive direction.
But can you do the homework question? It's kind of different than everything we talked about. The last one.
I thought we did that one.
No, the last one with the black hole. No, we didn't.
Is that was Sirius or something like that? Yeah. What was its average density be and all that kind of stuff? Density over volume? Remember, density is mass over volume, right? Is it that one?
No.
0.38? Oh, what would be the acceleration due to gravity at a distance of 2 Schwarz radii from the center of the black hole? Oh, well, we just did that. We just did that with problem 40. Same type of thing. All right. Well, let me show it to you real quick then. All right, problem 38 then. All right, so that's how you do relative velocities. All right? That's how you do relative velocities. It's kind of tricky, but it's not all that bad.
Finish the one where we subtracted.
What's that?
Is there one where we subtracted?
Yeah, the first one we did. We did that. Okay. Well, one was negative and one was positive. All right. Now, okay. Let's take a look at. It's just a matter of aligning your subscripts. All right. Let's take a look at that one problem, problem 38, because I got a couple emails on that one. Problem 38 says this. It says, what would be the acceleration due to gravity? Okay, so A equals gm over r squared. Okay, and basically what it said was, let's find the Schwarzschild radius of the sun if it went into a black hole. All right, if the sun crushed down to become a black hole, what would be its radius? And then it said to take, and then our r here is this equal to 6r. Okay? And our r is this equal to 6r. So the r that we find, r is equal to what? 2gm over c squared, right?
To find R, then we use the acceleration.
Yep, and then to find the acceleration, so we're going to find this r, then you're going to stick it in for the 6r. Okay, then you're going to stick this r, you're going to multiply it by 6 to find this r and stick it in there. Because that's what it says to do. It says due to a distance of 2. Oh, it's 2. You're right. 2. Of 2 of those guys away. All right? So in the first one, we actually found out, I think earlier, that, well, this would be 2 times 6.67 times 10 to the negative 11 times, what's the mass of the sun? Right. Or 1.99. Some places say 1. I just had a beat in to be 1.99 times 10 to the 30th kilograms. Okay. And that's going to be divided by 9.00 times 10 to the 16. And when you do that, you come up with about, 3,000 meters, something like that, 2,900 meters. And so you just multiply that by 2 and stick that, and then square it and stick it into there. Okay? All right. So that's how you do that. And then you just take, and then what you do to find the acceleration is this gm over 2r squared. I think mine was 6 on my homework problem that came up. That's why I had 6 in my head. Okay? So that's how you do that. That's how you do that. Just be very careful with your calculators and stuff. Now, let's talk about something else that's kind of cool. All right? And that's, got a question. If I take some ice, here's a good question. If I take some ice, let's take 1 kilogram of ice, because we really need to tie together this relativity with some of the stuff that you've learned in chemistry. All right? All right. Let's take 1 kilogram of ice. Got 1 kilogram of ice. I want to melt it. If I melt this ice, does it gain mass or lose mass, do you think? Pretty much stays the same. Can you detect it? No, you can't. But it actually gains mass. When something gains energy, it gains mass. Why? because E equals mc squared. So when I add mass to something, well, E naught, when it's just sitting at rest, so when I do my change to E naught, what's the only thing that can change? The mass. The mass is delta M times c squared. So how much, though? How much did this ice, how much mass did it gain? How much did it gain? And you'll find out, well, let's just go and crunch the numbers here. In other words, the Q, which is going to equal E naught, equals delta mc squared, which also equals, now what does Q equal? How do we melt ice? If it's at 0, and it's also at 0 degrees. We're starting it at 0, and then we're going to get a puddle of water. So how do we do that? Remember that? Yes, latent heat diffusion. There we go. Is equal to 1.00 kilograms times, anybody remember the latent heat diffusion for ice?
Isn't it 3,300?
Oh, it's 33,000. There you go. All right. Times 10 to the 5th joules per kilogram. Haha. I love it when a plan comes together. So what I'm going to wind up with is joules over here and joules over here. And then divide that. So my change in mass is actually going to be equal to 1.00 times 3.3, right? Times 10 to the 5th. I don't square this. Times divided by 9.00 times 10 to the 16th. Oh my. You can tell right away that this is going to be pretty small because this is 10 to the 5th and this is 10 to the 16th. What are we talking? About 10 to the negative 11 factor? It doesn't show up on normal things. What's that?
I don't think it'll show up on normal calculations.
Oh, really? It showed up on mine, on my special one. Right, I know. Because we're in the physics department. We're in the 2010s now. You know, we allow these calculators. Okay. All right, now, and so the other thing, one last thing, and then I think I'll just let you go. All right, because it's a nice day, and I'm tired of talking over the mower. Tingy's ready to leave. She's all done. This is the last time of videoing. All right. By the way, she's going to UCLA to work on her PhD. When are you leaving? In August, right? Yep. Okay. Work on fuel cell stuff. She's going to make a fortune with these. You're going to see her in, like, Entrepreneur magazine or something like that. Ting discover of efficient fuel cells. But anyway, you're going to say, I remember when she was videotaping my class. Anyway, here's another thing. Let's just figure out now. This is how, when all this was coming about in the 20s and 30s, okay, this is how things got really dicey and kind of exciting and everything else. If you want to read some fascinating politics where politics and science run into each other, read anything you can get your hands on the Manhattan Project. It'll scare the bejesus out of you. All right, and then afterwards, what happened is the Cold War that I grew. Most of you all were kind of post-Cold War. I mean, but you know, we had to watch all the little duck and cover films and all that kind of stuff in school. Yeah, told you to get under the desk, cross your legs, and kiss your ass goodbye, basically. But anyway, so all right, now, so let's figure out. So this is kind of the scary part. Let's see how much energy, just rest energy, is in a golf ball. It's got a mass of 0.05 kilograms. What's the rest energy of a golf ball? If we could release this energy, we'd have 0.045 times 9 times 10 to the 16. And I'm going to go ahead and crunch those numbers real quick for you. 0.045 times 9 second e to the 16. Boom. 4.05 times 10 to the 15 joules. That's a heck of a lot of energy. All right? That is a heck of a lot of energy. All right? If that was released rather quickly, so that's why with just simple, and hydrogen is, water is fun to play with, because you all know more than I do. You got hydrogen with what? 1 electron, hydrogen with 2, and hydrogen with 3 electrons, right? Am I right?
Yes.
Yeah, you got the deuterium and all that kind of stuff. Well, that's heavy water. And that's what the Axis powers and the Allied powers in 1940 were racing to come up with first, so they could release all that energy at one time. Because that's the difference, because energy, what makes an explosion really bad, or what makes an explosion is how much energy is released how fast, okay, and the concussive effects in the air and things like that. So if you could release this all in one shot, that's why a pound of chocolate chip cookies has more energy than a pound of dynamite, but it just gets released very, very, very slow. All right? But you can do the same amount of damage. You just give a 18-year-old boy or something a pound of chocolate chip cookies and a sledgehammer and say, there you go, and he could probably do as much damage as until he's used up all those cookies as dynamite. All right, we are done. We're done. I'll see you all early, bright and early Thursday. Or don't forget, review sessions Monday and Tuesday at noon if you want to go to those. And I don't want to hear about